Welcome to the Deep Dive Books channel, where we hope you find something valuable every day.
Let's continue with Max Bennett's A Brief History of Intelligence. This is the second part of our exploration. In this section, we'll discuss the first major breakthrough in the evolutionary history of intelligence, which occurred 550 million years ago, with the emergence of the first brain. You might assume that this brain was rudimentary, perhaps lacking in function. But on the contrary, it was quite advanced. The owner of that brain was the ancestor of all animals with brains today. In fact, many of our primary body structures, and even the basic functions of our brains, aren't fundamentally different from those of this ancient creature. I suspect that evolution discovered the optimal solution right from the start. This brain was so remarkable because it had to solve the same problems we face today. Finding food. In the previous section, we discussed corals, which obtain food by waiting for it to come to them. Their reflexive capture of food doesn't require much intelligence. But if you need to actively move to find food, you must know how to navigate towards it and avoid danger. The earliest single-celled organisms had this ability. They could swim toward food and away from harmful chemicals, using their built-in protein propulsion systems. But for multicellular organisms, with different body parts performing different functions, how do you coordinate and make decisions? Although the earliest brain was structurally simple, the design philosophy behind it was incredibly profound. Of course, we shouldn't say design. Everything is the result of natural evolution. But you can't help but marvel at the ingenuity of nature. Have you noticed that almost all animals have bodies that are bilaterally symmetrical? These are called bilaterians, and they make up 99% of all animals on Earth. The remaining 1%, like corals, starfish, and jellyfish, have radial symmetry and are known as radiatans. But why do these two body plans exist? You definitely wouldn't want to be a radiatan. They lack brains, with their intelligence being decentralized. More importantly, their digestive system has only one opening for both eating and excreting. The earliest animals, which appeared 600 million years ago, were all radially symmetrical. It wasn't until 550 million years ago that the first bilaterally symmetrical animal evolved. All bilaterally symmetrical animals on Earth today, including us, are its descendants. This first bilaterian was a nematode. It looked much like today's nematodes, resembling a tiny eel. It had a brain, muscles, a stomach, a mouth, and even an anus. Food went in through the mouth, and out through the anus, leading the way in the civilized life of animals at that time. While the human brain has 85 billion neurons, the nematode's brain had only a few hundred. It lacked vision, relying solely on its sense of smell to find food. Yet, despite its simplicity, the nematode could do remarkable things. A simple experiment will immediately reveal its intelligence. Place a nematode in a petri dish, with a small piece of food in one corner. You'll notice that the nematode doesn't just move randomly. It zigzags its way towards the food, following the scent. This mobility is closely linked to bilateral symmetry. For a radially symmetrical animal to move towards food, it would need sensory and motor devices in every direction, which is inefficient. In contrast, a bilaterian can move forward with just the ability to turn left or right, enabling it to go anywhere. All of today's transportation devices, from bicycles to airplanes to robot vacuum cleaners, are designed with bilateral symmetry. It's simply the best solution. With the ability to move, nematodes needed three basic skills to seek advantages and avoid harm. The first skill is recognizing what is good and what is bad. Food is good, while high temperatures, unpleasant smells, and bright lights are bad. But how do nematodes know this? This mechanism is implemented at the level of neurons. Positive stimuli activate positive neurons, while negative stimuli activate negative neurons. Neurons then vote on the information. If more positive neurons are activated than negative ones, the nematode knows it's moving in the right direction. Otherwise, it needs to turn or flee. The second skill is weighing options. Neurons detecting food signal that there's food ahead, but those detecting danger warn of a hazardous smell. So, should the nematode proceed or not? This involves two different dimensions that can't be directly compared. Life is full of trade-offs. This is why nematodes need a brain. The brain integrates information from all sides to make a decision. You can't just react to stimuli. You must consider whether the benefits outweigh the risks, or vice versa. To do this, you need a third skill. Understanding your own state. For instance, are you hungry or full? If the nematode is relatively full, it might avoid an area with food if there's danger. But if it's very hungry, it might take the risk. Hunger and satiety signals are transmitted through the body by releasing certain chemical neurotransmitters, broadcasting them throughout the brain for reference. With these abilities, you could build a robot vacuum cleaner. Dust is like food, hitting a wall is like encountering danger, and low battery is like hunger. But nematodes are still smarter than any robot vacuum cleaner we have today. Remarkably, nematodes have a learning ability called associative learning, which is essentially Pavlovian conditioning. If you ring a bell every time you feed a dog, the dog will associate the bell with food. The next time it hears the bell, even without food, it will salivate. This is an involuntary association, meaning you can't choose not to learn it, nor can you easily forget it. In a lab, if you play a sound, and then shock a subject's hand, after a few repetitions, the subject will instinctively pull their hand back when they hear the sound. Willpower doesn't help here. This is why soldiers coming off the battlefield might duck for cover at a loud noise. Even if you remove a mouse's brain, its body will still reflexively respond. Associative learning happens directly, at the neuron level, yet after 600 million years of evolution, radial symmetry animals never developed this ability. This skill is unique to bilaterians like us. It's because we face a more complex and changing environment, requiring us to consider more clues. And even for nematodes, their associative learning ability is quite advanced. For example, if a nematode frequently finds food near salt, over a period, it will associate salt with food. This is acquisition. Later, if the environment changes, and there's no more food near salt, the nematode's response to salt will weaken. This is extinction. After a while, if the nematode finds food near salt again, it will quickly re-establish the connection. This is spontaneous recovery. Nematodes also understand that the most useful clues often appear closest in time to a reward. If multiple clues are present, they'll prioritize learning the strongest signal. If a stimulus always appears regardless of reward, the nematode will mark it as background noise. Once a clear clue is found, the nematode will ignore other clues, because there's no need to consider them further. Bennett emphasizes that this is a continuous learning process. Nematodes never stop training, because their environment is always changing. By contrast, today's AI models all have a training cutoff date. After painstakingly developing an autonomous driving AI, if the government suddenly switches to left-side driving tomorrow, the AI will be at a loss. The most surprising ability of the nematode's brain is its capacity for emotions. For example, when you observe a nematode, you might notice that it moves slowly when it's full, as if it's content. But when it feels threatened, it swims rapidly, as if it's scared. These are emotions. You might immediately object, saying that these are just behaviors of the nematode, simply effective responses to external stimuli. Why call them emotions? Of course, we don't believe nematodes have conscious emotions, as consciousness is far more advanced. But we can still say that nematodes have emotions. The difference between emotions and just responding to stimuli is that emotions persist even after the stimulus disappears. For instance, if a predator tries to catch a nematode, and the nematode immediately flees, you could say, this is just a response to the stimulus. But if the predator quickly leaves, and the nematode is still panicked, still fleeing, how do you explain that? To some scientists, this is an emotional state. The nematode is enveloped by the emotion of fear. Why would evolution give nematodes emotions? Isn't this behavior superfluous? In fact, emotions are very useful, because the natural environment is full of uncertainties. Take fear, for example. When encountering the first predator, you should not only perceive the threat from that specific predator, but also recognize that the environment itself might be dangerous. If you're in a dangerous environment, even if that predator leaves, what if another predator appears? So, you should remain alert for a while. This is the role of emotion. Similarly, after discovering the first bit of food, the nematode should not only eat it, but also feel happy. Because if there's one piece, there might be more. Happiness will motivate the nematode to search harder, in the area. This is like how a robot vacuum cleaner should linger in a spot where it finds a lot of dust, assuming there's more dust nearby. Emotions make our behavior more persistent. We say nematodes have emotions because their brains contain dopamine and serotonin. Dopamine motivates animals to desire something and pursue rewards, while serotonin provides satisfaction and pleasure, allowing temporary cessation of pursuit. When there's food, dopamine makes a hungry nematode eat eagerly, even excessively. Once full, serotonin helps the nematode settle down. Isn't this emotion? What's even more remarkable is that nematodes can experience depression. This relates to their response to stress. Encountering a predator is acute stress, prompting a fight or flight response. Their brains release adrenaline and other hormones. Yes, nematodes have hormones just like humans. To energize muscles, halt energy-consuming functions, like reproduction and immunity, and release opioids for pain relief. Once the threat is over, nematodes need to enter a recovery state. Eating well, resting, and resuming normal functions. This helps them return to their usual state. Evolution has set this up quite well. If a threat persists, nematodes enter a chronic stress state. Researchers can simulate this by continuously stimulating nematodes for 30 minutes in the lab. Nematodes respond to chronic stress, similarly to acute stress, but with one key difference. They also release a lot of serotonin. Serotonin makes the nematodes lie down and become apathetic. In simple terms, nematodes become numb. This can also be described as learned helplessness. This is the most basic form of depression. Evolution's setup makes sense, because if there's a persistent threat, moving around recklessly could be more dangerous. It's better to play dead and wait, hoping the threat will pass. However, this mechanism has problematic consequences when carried over to human societies. Our daily pressures are not life or death. We don't need to fight or flee. Chronic stress can disrupt our bodily functions and lead to depression. While hormonal adjustments can help temporarily, overcoming evolutionary programming remains challenging. Nematode intelligence is the fundamental basis of animal behavior. Here are some sophisticated behaviors that, in reality, any bilaterian with a brain can perform. 1. Seek benefits and avoid harm by adjusting direction, not just moving forward. 2. Integrate information and weigh various factors before making a decision. 3. Continuously learn and adapt. Don't stick to old habits. 4. Display behavior that reflects emotions. Maintain consistency rather than being indifferent. This may be the basic logic of survival for animals, a strategy refined over 550 million years of evolution. That concludes today's content. In the next part, we'll explore the revolution of learning.
If you feel there is value in this, please like, subscribe to this channel, and leave your thoughts or suggestions in the comments section. Let's grow together and read more good books.